Close this up.
Okay,
YouTube.
I think yes, I can. Yeah. Okay, good. Yes. Nice. Faster. Wow. Yeah. Good afternoon, PCS members and friends. Today we have a seminar by Dr. Mikhail Fistul, and Sergey Flark will introduce our today's speaker.
Yeah, okay, so welcome everyone. It's a pleasure to have Dr. Mikhail Fistul with us again. Let me tell you a few items from his CV. Mikhail did his PhD in 1984 at the National University of Science and Technology in Moscow, and his thesis advisor was Professor Aslamazov. After that, he worked for some time at the same, I think, institution in Moscow, and then he moved in 91 to Purdue. How do you pronounce it correctly? Purdue University in West Lafayette in the US, where he stayed for an extended period, 5 or 6 years. Then he moved to Germany, where he was an Alexander von Humboldt Fellow at the University of Erlangen, Nuremberg. Then he moved for a few years to work at the Max Planck Institute for Physics of Complex Systems in Dresden. This is where I think we met, not for the first time maybe, but where we spent lots of times together and also had joint projects. Then he moved back to Erlangen and as an invite professor, and then after that essentially he moved to Bochum with other interesting twists in the trajectory. He stayed in Bochum ever since. Then I should also mention at some point he actually came to Korea. So from Bochum to Korea, but then he went back to Bochum, so he really likes Bochum. And so he worked here with us at IBS for 2+ years. And yeah, he's an expert in superconductivity, in Josephson junction physics, quantum computers, qubits, and such things. And today he will talk about PT-symmetric arrays of interacting qubits. So the floor is yours. Let's welcome the speaker.
Thank you very much for nice introduction, and it's really a great pleasure to come back to this nice center. And today I would like to speak about the parity time as symmetric arrays of interacting qubits, and or shortly PT-symmetry. And first of all, I would like to stress the end of this title with question mark. And why is that? We will see during my talk. And then the system of interest is drawn as a cartoon here. and mostly it's a set of building blocks, PT-symmetric non-Hermitian qubits, two-level systems, specially prepared two-level systems, and interacting, which interacts with each other. And this work has been done at Ruhr University Bochum in collaboration with a nice team with this university, Ilya Ryumin, Benedikt Pernak, Yana Komisarova, and Grigory Starkov, who is right now on the University of Germany. Okay, this is outline of my talk, and first extended introduction, motivation for study this system, experimental and theoretical motivation.
Ignore.
Okay, and then I will introduce system of interest, PT-symmetric non-Hermitian lattice of interacting qubits, and discuss different systems. And I will focus on collective quantum phases and quantum phase transitions, phase diagram for this system. And then, maybe most interesting part of the talk is how we can produce well-known procedure of quantum annealing with the network of PT-symmetric non-Hermitian lattice. What is the advantages of this in respect to standard qubits array? Okay, first I start with the general things. What is PT-symmetry? And most important, I will speak about parity transformation, which means the change of sign coordinate, and time transformation reversal. It means the change sign of time. Interesting story, if you speak about fundamental physical laws, it's all time we have parity time symmetry. For example, special relativity theory, we have Lorentz invariant this interval, and if you change x to minus x and t to minus c, we have conservation of this. And also, if you go to electrodynamics, we will see what happens. T to minus t and x to minus x, if you have refraction index, has also parity transformation, everything okay, and fundamental physical laws satisfy to parity time symmetry. But we can say fundamental physical laws are extremely fragile for different things like friction, losses, and most important for electrodynamic, imaginary part of the refraction index. In this case, the especially time reversal is broken, and question is it possible to some optical system, for example, recover PT-symmetric situation? The answer is yes. And how it happens? We have nonlinear optical media with optical gain and loss. How it works? It's drawn here, and most simple case, we have two waveguides with some interaction, and one waveguide is in equilibrium condition. We have losses, optical losses here, but another part works like so-called parametric amplifier. We applied additional pump to this system, which produce optical gain, which means the amplitude of this wave inside of this increases with time. And then this gain in this part compensate losses here, and due to this interaction, we can think about this simple system as a two-level system. one excitation of waveguide here, and another is here. Excitation of wave, and two-level systems, interaction, and also one part with a loss, another with gain, and which produce this very famous Hamiltonian in this system, which can be written in spin matrices with X and Z, and we have off-diagonal element this, and diagonal element, which is with imaginary part. Okay. This is possible to realize, and everything okay here. But question is it possible to transfer these ideas and this language to quantum mechanics?
Okay, before we move on,
Yeah.
why do you need nonlinearity in this picture, which you just showed?
Because you cannot prepare gain without nonlinearity. This is point. Because for produce gain, you need parametric amplifier, parametric excitation. It means you have refraction index is nonlinear. You need at least kernel nonlinearity.
But then the mode in which this, or at least the Hamiltonian which you write down, and which the other people were writing down on PT invariant systems, is usually starting with linear systems. So the equations themselves, which you use to explain what's happening, are not written in a nonlinear.
Okay,
But what you say is in order to actually get gain, you need some kind
if you would like to realize this Hamiltonian, it's most important question how to realize this Hamiltonian. If you go to optical situation, optical media, and classical optical media, to realize this type of Hamiltonian, you need nonlinearity, plus you need non-equilibrium condition produce gain.
Sorry, may I also some experiment? Sorry, you mentioned this parametric amplifier to get this gain effect in this optical system. I wondered, for example, the Josephson junction is the nanoscale device. Can you also use this parametric amplifier to get this loss and gain effect?
Yes, yes. The answer is yes. You can, instead of waveguide, optical waveguide, if you go to microwave region, you can use one Josephson junction, applied pump and everything, this produced amplifier, and another Josephson junction without anything, and then you can combine this and produce this optical object, which works similarly with this equation.
Excuse me, do I catch correctly that the nature of gain is not that important? This is why this question on nonlinearity of the medium is not in fact.
But
as I understand, for example, you could have gain by some electrical injection, for example, from electrons and holes which have stimulated scattering into some optical mode, and this would work in the same way.
yes, yes, it's possible. It's I can say if you look on different platforms, and but in electrodynamics, beyond quantum mechanics, and electrodynamics, you can produce for acoustic, for different values of different platforms, and you need produce gain. Then question is how produce.
Just an engineering.
Yeah, just
engineering. Some.
But I can say first realization was with this scheme, with the maybe. First realization. Okay. But then, what happens in quantum mechanics? In quantum mechanics, we also can say about parity transformation, x to minus x, and time transformation, which means I to minus I, and look on Schrödinger equation and say some condition for Hamiltonian, which produce PT-symmetry, satisfy this commutation relation. And first answer was 100 years ago, and for founders of quantum mechanics, they say Hamiltonian is just Hermitian operator, and in this case, automatically we have parity time transformation, which is all quantum mechanics satisfies.
Where you mean that the Hamiltonian is invariant under parity
Yes.
itself? I mean, if it's
Yes,
not
if-
invariant,
if- if-
yeah, if it's not
yeah,
then okay.
Okay, and this means, again, question is, quantum mechanics is extremely fragile, dissipation and decoherence, and question is, how can we realize PT-symmetric non-Hermitian quantum mechanics? It means what happens if we abandon condition hermeticity for Hamiltonian. For example, we can see some harmonic oscillator. This is Hermitian operator, but then we can imagine non-Hermitian system like this, and definitely this is PT-symmetry, but not Hermitian. Okay, and then due to this Carl Bender and his student, and there is realization of this idea. What happens if we just produce some brain games, just abandon hermeticity of Hamiltonian? Again, for simple system, like a single two-level system, we have this type of Hamiltonian, which is PT-symmetric, non-Hermitian, and what happens for this case? And very simple to diagonalize of this, and they found very interesting feature. Energy of this Hamiltonian can be real, like Hermitian Hamiltonian, or complex conjugate. And then people classified if we have this range of parameters, we have real part of eigenvalues real, and non-zero, and imaginary part is zero. It means people call this PT-symmetry preserved quantum states. And another range of parameters, situation quite opposite, real part is zero, and we have two complex conjugate eigenvalues. And people called PT-symmetry broken quantum states. Again, I stress, Hamiltonian is PT-symmetric, but state PT-symmetry preserved and broken. Broken means eigenvalues complex conjugate.
No, I think it's just bad wording. I mean, come on, the Hamiltonian is invariant under symmetry, the matrix, the
We have
eigenvectors
to distinguish two states.
the eigenvectors reflect the same symmetry eigenvalues as well.
Yeah.
So it just can so happen that they are even better than that. Yeah,
Okay.
they have more symmetries than you expect.
This is only eigenspace, so that's on the basis. Maybe if we run time dynamics of the Hamiltonian, the T-symmetry will be preserved.
Okay, we have diagonalization of Hamiltonian, and we have eigenvalues. And if eigenvalues complex conjugate, this is this is specific quantum state.
I mean, that's still a consequence of PT symmetries.
Yes.
Just that they are
Yes.
complex. So
Yes.
you don't break the symmetry. I mean, it's
No,
not
no.
there. It's just that your eigenvalues are not
Mhm. Okay, and then the parameter which separates these two different types of eigenvalues is called exceptional point. Okay, and then what is the next step? And first question again, can we realize this type of PT-symmetric non-Hermitian quantum mechanics in a single qubit? And second question, what happens with different quantum phases if we have specially extended system, interacting system, for example, interaction of spins, bosons, fermions, interaction of qubits? And first question, the answer is yes. And second question is still with question mark. Okay, what means yes for experimental realization of single qubit PT-symmetric non-Hermitian qubits? And people produce with different methods, at least 2-3 methods, different methods how to realize this. Idea is the following. You have not a single qubit. You have two interacting qubits. One is a working qubit, this, and another qubit called Ancilla qubit. And we have interaction between these two, and we have time-dependent interaction between these two qubits. If you properly produce time-dependent interaction, the work of a working qubit with this Hamilton. The total system definitely Hermitian, but one part of this system works with this non-Hermitian Hamilton.
So you see, the total system is still Hermitian.
Yeah.
But then that doesn't remove the problem you mentioned at the beginning, that symmetries are highly sensitive to perturbations. So that is not really.
No, it's, you can prepare for time quantum dynamics of this part of this system satisfy this non-Hermitian.
No, I understand that. I'm just saying that this doesn't remove the problem which you mentioned at the beginning, which is that you want to find a way to have stable dynamics, despite the fact that hermiticity or anything else, all kinds of symmetries can be actually easily destroyed by dissipation and other.
Oh, okay. You mean I cannot prepare equilibrium? Actually, I cannot, I don't know the way, to prepare the total Hamiltonian in a non-Hermitian way.
We can discuss it.
Okay. Okay. Because what people really found in this case, they applied this Ancilla qubit, the working qubit, and then they measure in time dynamics of this probability to find a low state or upper state for this working qubit. And then they see if we prepare this type of Hamiltonian for working qubit, they found oscillations for this type of parameter or just decay, which indicate transition between one type of states with real eigenvalues to stay with eigenvalues, complex conjugate eigenvalues. This transition. And specifically on this point, we have different types of decay in respect to this.
Sorry, the question in your previous slide, is the eigenvalues as a function of the ratio between gamma and the delta. The
Gamma.
gamma R, yeah,
Ah,
here.
okay.
It seems
Okay.
that here, as you increase this ratio, this non-Hermitian effect increase. But in your previous slide, seems that the decay rather suppressed as you increase this ratio.
No, I can say, in this case, if gamma is small, we have oscillations.
Yes,
If we have gamma is large,
large.
we have decay.
Yes.
Decay. If gamma equal delta, is some exceptional point, specific decay. It's still decay, but different, not exponential decay.
That explanation.
Sorry, I don't get it. So you have gamma larger than delta, and one of your state evidently decays, but another one blows up. Why you
Why?
don't see it?
Okay.
In
Yes,
experiment.
in complex conjugate, we can see this situation. It's in spite of this, one block. Okay, point is, I can explain. Because it's still probability to find one or two states. It means you have, formally you have enhancement in numerator and denominator also. In fact, and
like this.
okay, this mathematical way.
So you mean some normalization and
Yes,
then, yes.
yes.
Okay.
This is because still measurement is the following. You can see probability to find system in a zero state or upper state. And it cannot be larger than one.
Okay.
Yeah, I can image the R comes from the transition rate between two states.
R?
Yeah.
No, R you can prepare specifically due to this procedure, time-dependent interaction between Anchila qubit and working qubit. You prepare this. And then for fix this parameter, you measure. And then for R small, you have oscillations, or for R large, you have decay. You can think two ways. And one is just if you prepare this Hamiltonian and then see what happens with your probability to find one state or another state, with Schrödinger equation and so on.
It means R is the transition rate between two.
Not,
No.
because it's an imaginary part. If you have situation like this, if it's real,
Total system is a Hermitian.
total system is a
minimum R.
okay. R is a total system is Hermitian, but for part of the system, you can prepare this non-Hermitian Hamiltonian. Non-Hermitian Hamiltonian.
Yeah.
Okay,
Okay.
and physical meaning of this parameter is non-hermiticity, because population increases on.
The question is that since your whole system, as you stressed, is Hermitian, R must also have some meaning in the whole system. And what is it there?
Okay,
This is some kind of like projection onto.
It's yes, it means some kind of interaction, effective interaction between Anchila qubit and working.
And another question: what are the units of time there? It says time in units of t, but what is VGT?
Okay, it's
milliseconds, or what are the systems?
it's standard qubit time. It's okay. It's time. I think it's microsecond.
Okay.
Microsecond.
And back again to this issue. So you said that there's a protocol which is time dependent.
Yes.
Well, that makes it non-Hermitian, doesn't it? Because you have a time dependent system. So your Hamiltonian kind of becomes time dependent, or what am I getting wrong?
Total.
You have two qubits,
Yes.
but their coupling is time dependent. And that means you have a non-Hermitian Hamiltonian, in general at least. So it's not even the whole system seems not to be Hermitian then, or what am I? Or what?
No, I'm,
You see my point?
I'm
You have a big system and you say time dependent. Okay,
time
so-
dependent. Why it's not a remission?
I don't know.
I don't know. It's if inside of
Oscillations.
What?
Oscillations or
no, it's
can have a time.
I don't know.
I mean.
I'm asking you guys, so if.
no. If you have time dependent Hamiltonian, and it's still a remission.
Yeah.
At each moment of time, your matrix is Hermitian.
True.
Yeah.
You have, so,
No, it's still a remission.
so you have actually a Floquet system. Then
Yes.
you should say you have a Floquet system.
Yeah.
But I think it's still a remission.
Yeah.
Okay, we can discuss that later. Okay, and this is another method how to prepare the system, and just to use instead of two levels, to use 3 levels and different rates,
Там локально можно время.
relaxation rates of different levels, and some clever way how to still produce non-remission
Конечно.
part of this Hamiltonian. And again, the same story, and people found two different, one relaxation and another oscillation, and different type of behavior, broken state, unbroken state, and transition. Okay, and I will little bit speed up, and this is I just attract your attention how to prepare another non-remission system with the help of so-called dissipative Aronoff bomb cage, and we have one part which is mostly bosonic system with dissipation, and another with just hopping between bosonic sites. And then we can produce famous Hatana-Nelson model, but still realization of this without interaction between processes. Okay, and
Sorry, why there won't be interaction?
okay,
Don't get it, because there is some repulsion, and it's not.
okay, because for this realization, I just add this term because it's possible to produce some interaction definitely for each side. Okay, but realization in this paper, it was without interaction.
It seems like some miracle for me. Why?
For ultra cold atoms,
So they just tuned some parameters in the atomic system, like Feshbach or something, and then get some very small interaction, negligible.
yes,
With absence of
But
interactions.
in any way, in this experiment, in this paper, they do not discuss interaction between bosons, even on site interaction.
Oh, okay.
No,
That they didn't discuss, but it can be there. Right?
yes,
Right?
yes.
Oh, okay, then I totally agree.
Okay, and then
And where is non-reciprocity coming from this setup?
okay, it's they say if you have only a single side dissipation, and then you have some combination of this hopping strengths with some flux, additional flux, then they say this is non-reciprocal transfer. And this parameter gamma depends on flux and all this stuff. Okay.
So let's see where the non-reciprocity comes from.
Reciprocity on this line.
It is induced by gamma, right?
Induced by combination gamma and T0 and this different different hopping.
No, look, if the hoppings are different, but by themselves reciprocal, then if gamma is 0, then you just have some nice system, and there's no non-reciprocity.
They say
So non-reciprocity. Can we see that in the equation somewhere there, where this Non-reciprocity pops up. Is it the second line or the first line? Or
No. The reciprocal is here and here, minus and plus.
Okay, and gamma tilde is what?
Gamma tilde is
Something related to.
this three parameters. Okay. But definitely you need one single side dissipative.
What is CMA and CMB? A and B are the
bosonic.
No, A and B are the bottom sides.
Yes,
there, no?
yes.
Mhm.
Sorry for another question, but so they really observed some accumulation of bosons in one side of the chain here?
Yes,
Right? Okay.
I think so.
Which means interaction should be robust.
Yes.
Okay, and just mention standard Hermitian qubit set. People can prepare arrays of qubits and then produce different types of Hamiltonians, spin type of Hamiltonians. This is completely Hermitian. And for example, here 20 or 30 sides, and next case is 1000 sides, huge lattice of interacting qubits in the world of Hermitian. And then question is it possible to combine idea and realization of interacting qubits, network of interacting qubits, spin Hamiltonian, and PT-symmetry induced for single qubits? Okay, this is another type of another type of brain games. Quantum dynamics of PT-symmetric non-Hermitian qubit networks. And where we have combination of interaction between qubits, and we have each building block is a PT-symmetric qubit. And we have Hamiltonian for this system, which contains two parts. One, interaction between qubits. It's Ising type of interaction or exchange type of interaction, and local part for each building block. We have off-diagonal element, we have on-diagonal, main diagonal element, and also this type called staggered PT-symmetric non-Hermitian part. Why staggered? Because if we have abundant this -1 power n, we have PT-symmetry only for epsilon equals 0. If we have general case of epsilon, which is qubit bias, and we need to look to conserve PT-symmetry, we need this staggered PT-symmetric non-Hermitian part.
Sorry, but J2 is also of n minus n, right? It's just a typo there.
Yes.
J2 of n minus n.
Yes.
Okay. And you really need some long-range interactions?
No,
or they're
that's just for generic purpose. Yes.
So like on the picture, it will be just nearest neighbors. Oh.
For this picture, for cartoon, yes. Yes. And then we look on this. Actually, it's not necessary because for Ising model, we have just constant and we can see. Okay, it's this is first example. We have PT-symmetric non-Hermitian transverse field Ising chain, and this system, which is if this system is Hermitian, gamma equals 0, we have integrable system. In the presence of gamma, we have non-integrable system. And we can see what we can find from this interacting system. Interesting.
So, excuse me, could you please return to the Hamiltonian from the previous slide? So this -1 to the power n -1 means that we have gating and dissipative speeds in this chain.
Okay, it's just a reverse. If you have, for example, a lowest level for qubit with dissipation, and upper level is with enhancement of population, and for second qubit is the reverse. It's just
So up and down.
Yes,
of
yes,
spin, up and down
Yeah.
space of spin
Yeah.
correspond to gain and loss, and
Mhm.
vice versa for
Yes.
his two neighbors.
Okay, and then we can see what we can do. And actually, we take eigenvalues, the organization of Hamiltonian, and to see what is the range of parameters where we have complex conjugate and exceptional point and real eigenvalues. And what we see, this is some very interesting point. We have, for some range of parameters, we have crossing points, different types of crossing point. For example, here, and we have here, and also here. It's Hermitian case, Hermitian case. But then what happens if we introduce non-Hermitian part? Non-Hermitian part. We will see, for example, this part produce exceptional point instead of crossing point. And then eigenvalues, complex conjugate eigenvalues in this area. Also here, we have exceptional point, and then this area, which is decline, means we have complex conjugate. But here, not. We have this real eigenvalues, and this is but also real eigenvalues. Idea is, what happens if two levels cross each other with difference or the same type of parity symmetry? This is answer. For example, here, for gamma equals 0, we have one level with a parity positive and another with negative, and then we have exceptional point. If we have the same parity, we have no exceptional point. This is some symmetry consideration and interesting.
Of chain. What's the length of chain you consider?
Excuse me?
Length of the chain.
Of size.
Okay, this is just to have more nice view. This is 4 sides, but actually what we can see here, because we put 18 sides and produce exact diagonalization and construct phase diagram for different phases, and this is a zoo of phases, because previously it was just paramagnetic phase, ferromagnet phase, and transition and antiferro. Here we have symmetry preserved, symmetry broken, and this point is exceptional point, a line of exceptional points. And this is collective phases and phase diagram for this system. Okay, and another thing to understand the zoo of these transitions, we can, and phases, we can look on integrable model when parameter delta equals 0 and we have exchange type of interaction. And still we have this transverse field, a staggered transverse field, but in the presence of real parameter epsilon. And this Hamiltonian, we can diagonalize this with the help of Jordan-Wigner transformation, produce fermions, and due to staggered field, instead of standard case when we have one band, here we have two bands, but still fermions not interact to each other, and we have two bands problem. And diagonalization of this, and then question is, what is the filling of this all eigenstates to produce ground state? And it's possible also to see this, because ground state is just real part of eigenvalues is less than 0. Interesting point, definitely for some value of k, we have complex conjugate eigenvalues, and for another value of k, we have real eigenvalues, and we have to look at what happens with the filling factors. And finally, we obtain shift of, in the presence of gamma, we have a phase diagram and shift of critical point. And instead of for gamma equals 0, we have critical point 2 and minus 2. And here we have collapse of this point. And for large gamma, we have only Mott insulator state.
So you have two bands because of that -1 to the power.
Exactly. Okay, and finally I have.
Sorry, I'm kind of lost. What do you mean by Mott insulator phase here? You have some, in spin language, you have some bond order. What's going on?
Mott insulator in the language of bosons, definitely spins you can produce like hardcore bosons, but in fact it's just a paramagnetic state.
Okay.
Because it's epsilon for gamma equals 0, you have we have for epsilon it's very large. It's very large. All spins in z direction.
Okay, yeah,
And-
I got it. Okay.
All spins in z direction, and if you introduce gamma, it's also this area for large for epsilon starting already with epsilon equals 0. You have you have in one direction.
And in fermionic language, you said that you need to populate states with real part of energy smaller than 0. And this is possible to have this as a stationary state because you can have only complex conjugate
Yes, yes.
eigenvalue.
For complex conjugate eigenvalues, you have filling both states.
You can, okay.
It's property of PT-symmetric.
Interesting.
Exactly. Okay, and then I will go to this part, quantum annealing. And first, what is the general procedure for Hermitian qubits? We have initial simple Hamiltonian, and then we have final complex Hamiltonian, and then we have interpolation with some time-dependent parameter of this. And the idea is we start with a ground state of initial Hamiltonian, which we know what is rather simple. And then if we tune parameter S with some kind of close to adiabatic, we have to find also with some probability final ground state of the final Hamiltonian. If you have infinitely small velocity, infinitely small change of S, velocity, speed of S, we definitely will come to ground state of final Hamiltonian, but question is, what is the time we need for that? Okay, and then this is well-known Landau-Zinner model, Hermitian case, and we can see what happens. And everything depends on off-diagonal element and the speed of changing parameter S. Okay, we will see, important to see some instantaneous energy spectrum, and we see some gap between this, and then we change very slowly change parameter S with some speed, and we see what happens. Most important, if gap is 0, we never come to the ground state. Okay, the all time system goes up, and we can produce very nice color plot. Here we have 1 divided by total time, and here we have parameter of diagonal element. What is important, if even very slow changing of parameters, we still has 0 probability to go to ground state. ground state. And then we go to quantum annealing with PT-symmetric non-Hermitian networks of interacting qubits. Idea is, again, we have some initial simple Hamiltonian, and we have final complex Hamiltonian, but interpolation with PT-symmetric non-Hermitian Hamiltonian. But what is important, non-Hermitian part keeps constant. It's no this part, ST. It means parameter R we keep constant, does not change. And here we have this type of procedure, the same story as this. And again, we start instantaneous energy spectrum to see what is for this particular case. We have initial Hamiltonian, very simple, like this. And we have Hermitian part. And then we have more complicated final Hamiltonian for two interacting qubits and non-Hermitian part with staggered coefficients. Okay. Then we see what happens. For epsilon equals 0, and for Hermitian case, we have no gap at all. Specifically, we take this system where standard quantum annealing does not work. And then if you take non-Hermitian part, we have this type of instantaneous eigenvalues as a function of S. We have area where complex conjugate eigenvalues. And if you increase gamma, this area increases also. And separated with two exceptional points. And more interesting case, if you introduce epsilon, we see zoo of different instantaneous energy spectrum. For this case, again, we have some gapless state and so on and so on. Okay. Then we have to try to apply quantum annealing. And what happens in this case, we will see for epsilon equals 0, this level and this level practically does not change. But these two levels vary with producing this specific area with complex conjugate. It means instead of 4 levels, we can produce 2 by 2 effective Hamiltonian. Like this, and we see most important properties of this 2 by 2 Hamiltonian with this no gap for gamma equals 0 and this specific area for broken states where we have 2 complex conjugate eigenvalues.
Oh, yeah.
Mm-hmm.
In the specific reason for the floating symmetric reason, what happened in your system?
Okay, in this system, if you stay here, just fix parameter S, you will see this 2 complex conjugate, and we see time dynamics is if you prepare a specific initial state, you will see just decay. If you stay here, you will see oscillations. Okay, but question is, what happens if you do not stay with particular value of S, but you change parameter S with some particular speed? With particular velocity, you change from S here and slowly change, go to this area, and then go here.
But
It's a Landau-Zinner problem.
Decay. In the red reason, the 1 qubit decay.
This is in these 2 eigenvalues complex conjugate. It means if you fix parameter S, you have dynamics is just decay for probability.
Yeah.
Okay, but if you stay here, oscillations. But it's not clear so far what happens if you do not stay, you just change parameter S from this part to this, and finally here.
Very slow.
It's slowly or
During the algorithm, they decay.
okay. It's we will see. We will see what happens.
One more question.
Yeah.
In the effective Hamiltonian, where is the time dependence?
Here,
Yes, so that
S is a function of time.
and that SCR or S.
No, this is constant.
That's just a constant.
It's constant is just the S is a function of time.
So the full Hamiltonian is still Landau-Zinner form. Meaning.
Is this Hamiltonian? Is yes. This is instantaneous spectrum, but in the presence of time dependence, it's Landau-Zinner form. And this is practically final slide. And what happens with this case? And for example, we have this spectrum Hermitian case, and definitely we will state to go to upper state. Upper state, not possible to go to this state. But what happens in general this situation? We will see different speed of changing. And we will see situation like this. We have some kind of oscillations, and then we go to a case when probability to find ground state is 1/2 in this case. And if you go to with some low speed, if you go to with a little bit higher speed, you will see some larger probability to go to excited state. And finally, this is plot, and we will see what happens. If gamma equals 0, no possible to go to ground state. This is 0 probability. But if gamma is 0.1, we have rather large probability, not large, 0.5 probability to go to the ground state. This is, this is how Landau-Zinner problem works with this PT-symmetric non-Hermitian case.
Seems to look similar to the previous color plot which you showed for the.
But there is again.
Can you show the previous plot again? Maybe just to understand what the difference is.
Difference is a different parameter.
You plot different things, right?
Yes. Okay. Here is a D, the gap, real gap here, but in fact,
and there you plotted gamma.
Its point is no real gap. It's there is exceptional points and this specific area. Yeah.
But here it is maximally 1, and there it's 0.4 only 0.5. Yes, in the second case.
Yes.
So
this is
kind of crucial difference.
This is situation is like this. For non-Hermitian case, you cannot go to with a probability 1, and moreover, you cannot go to ground state with a probability larger than 0.5.
So it's very bad for quantum computers to.
I don't. No.
No?
It's I can say 0.5 from some point is enough, because you have you can produce many times. And then you know this ground state is smaller, and you know what is a ground state. It's but definitely it's not like good to have 1. But point is, for real system, your gap is extremely small. This is most important problem for quantum analysis. This is and this is some way. Good or not, it's a different story, but it's some way to abandon these problems. Okay, and this is final slide and summary of this talk and next outlook on this. But I would like to finish this cartoon and about networks of Hermitian qubits. This is my favorite picture, and how it looks this field in 2000 and 2025 is really mature this area, and we have for PT-symmetric non-emission qubits 2025 we have production of single PT-symmetric non-emission qubits, and question is when we have networks and level of like emission qubits, they don't know. This is question. Thank you for that.
Okay, thank you for this nice talk. Questions?
May
Yeah, please.
I? The question not about the network, but some single qubits, including this non-emission lipid considered. I wondered, in typical superconducting qubit, for example, the suffer from decoherence dissipation due to the mass. If you include this non-emission and then calculate, for example, the relaxation rate, then this non-emission coefficients somehow modified or affect this relaxation rate.
Okay, and it looks like it's okay. First idea, like in optics, you can balance loss and gain and compensate somehow dissipation. And similar idea, of course, in quantum mechanics, in qubits stuff. And I can say right now it's not clear. It's really observed better results from dissipation. For example, I cannot say from this experiment situation is. Okay, and this type of oscillations in a non-emission type better or the same like standard qubit. I don't know, but definitely from general point of view, it looks like maybe it's possible to use like correction errors.
If there is some
because you have compensation of compensation of errors, and maybe it's possible, but it's still too early to say how it's.
For example, in your calculation, gain and loss are balanced, but you can tune, for example, the gain.
Yes, this is really compensation of losses. But unfortunately, directly produce amplifier on qubits. It's impossible method because you have all correlation properties of losses and photon field are different. You cannot use method of gain for a single qubit. You have to produce some more sophisticated technique, and then is it possible to compensate dissipation or not? It's an open question.
The real dissipation. So in other words, these non-emission or PT invariant experiments on qubits are still suffering from the same decoherence problems as the good old.
I can say this experiment very encouraged because they use real dissipation rate gamma F and gamma E is for different levels in clever way, but then can still observe this different phases, but I don't know. I cannot say this is completely compensated, but definitely they have different dissipation in respect to standard gamma F and gamma E subsequent. Yes, but still it's encouraged. But
here, It's not clear what is parity symmetry in this system. And because the symmetry broken due to this higher levels, but
Okay, then they have a difference between gamma E and gamma F. It means we have difference parity between these two levels, upper level.
you mean the wave functions?
Yes, yes. It's, you can, if you prepare different rates, and especially rate gamma F with this condition less than gamma E, you can produce some work only these levels. There's some oscillations between excited level and upper excited level. No ground state in this.
More questions? Doesn't seem to be the case, so let's thank Misha again. Thank you. And there should be food outside.